At the end of yesterday's lecture, I made a terrible mistake, and some of you have already noticed. I didn't turn the normal into a unit normal by dividing by its magnitude. Several second period people pointed that out. It's just one of those classic mistakes that students make, and you think, oh, how can they possibly make this mistake? Everybody knows it's a unit normal. And then, there we go, I did it. Is my microphone plugged in? Oh, well. It would have been picked up, just not very well. If I stand directly over and I don't block the microphone with my hand, the audio is not too bad. But as soon as I move away, I will use my hand to write. Okay, let me plug it in. There we go, microphone's on. Okay, so that's supposed to be a unit normal. So I've corrected it in the notes. So these are the notes that are currently up on the Vuller site, but of course the recording will be wrong. Now the recording software that I only use very shallowly. I record and I export, but I know you can do funky things like put text boxes over it. So I'm going to go in at some point when I have that mythical thing called time and put in a little box in the video that says, by the way, this is wrong. So I'm afraid that the video ends with an error with me not putting in that. But it is supposed to be a unit normal. So those root 14s end up cancelling out. That frequently happens. Doesn't always happen, but it very frequently happens that you end up with your scaling factor, your conversion factor, which is the root 14 that's in the numerator, cancels out with the modulus of the normal. It's quite frequently happens. Question? Yes, the answer is still correct because I read that from my notes, and in my notes I hadn't made that silly mistake. So the 21 is still correct. Okay, so I apologize deeply for that. That was a very shameful error. If somebody notices during the lecture, you know, a lecturer can always kind of spin that. You can say, oh, I did that on purpose to see if someone would notice. But when it's only pointed out in second period, then, yeah, that's a bit obvious. Okay, all right. Now, so now I'm going to do an example that's actually not in the handbook because I decided that the one in the handbook was too boring. The one I was going to do was 34. But instead of that, I'm going to do one from 2 years ago. So, MAM 2015, past test 2. So this is up on our bulletin. Question is, and it's question 2, S is that portion of the surface x squared plus z squared equals 1 in the first octant. So we're going to end up with a picture here that looks quite a lot like question 28's picture, which quite a few of you have already worked through. Lying between and x plus y equals 2, oriented upwards. Determine the flux of v, so that's our velocity field, across A. If v equals 1 over x, oops, excuse me. If v equals 1 over x, y, 5. There we go. So that's a flux question. All right. So, let's have a look. I can already start off by saying flux equals integral over s v dot n ds. Catch up with the stylus. Yep. Right. Over s v dot n ds. And I'm going to need to draw a picture because I need so. Okay, so here's an important thing. When you do a flux calculation, you are going to use your surface equation twice in 2 different ways. The one way is you're going to get your conversion factor. And for your conversion factor, you need to make one of your variables the subject of the equation so that you can work out your two derivatives. All right? But the other way you're going to get other way you're going to use your surface equation is to get your normal, is to get that n. And to get that n, we're going to work out the three-dimensional, three-component vector grad of our surface. And for that, we need to have all the variables together on the same side of the equal sign. So you'll use your surface equation twice in two different ways. One to get your normal, one to get your conversion factor. Your normal requires all the variables be together on the same side of the equal sign. Your conversion factor requires that you make one variable the subject of the equation. Okay, all right. So, S, let's draw S. Okay, we have this thing that would dearly love to be a cylinder running parallel to the y-axis, but it's being interfered with this plane, x plus y equals 2, so we end up with a surface that looks like that. So that's S. That's S, okay? And that's a 1, and that's a 1, and that's Z, and that's X, and that's Y, and that's a 2, and that's a 2. Very similar picture to question 28, the dimensions are just slightly different. Okay? So I am going to project that surface down onto the XY plane. Projecting onto the XZ plane is useless to me, because if I project onto XZ, I am going to get just a curve. I'm not going to get a region. And there's nothing wrong with that, but it's not useful for the purposes of a surface integral. For a surface integral, we need to project onto one of the coordinate planes such that we get a region. We get an area that we can color in. Okay? So XZ is useless. YZ's fine. If I project onto YZ, I'm going to get a region that looks like that. And that's fine, but we're going to need to work out the equation of that funny little curve over there. That funny little curve on that YZ picture is the YZ projection of this curve here. Okay, I'm going to draw it in red, and then I'll delete it again because I don't want it in the final notes. But that red curve that I've just drawn, that funny little curve over there in the YZ picture is the YZ projection of that little curve. And that red curve, which I've just now deleted, is the curve of intersection between your cylindrical surface and your vertical plane surface. So you'd have to take your two surface equations and eliminate x from them in order to get the YZ projection. So there's absolutely nothing wrong with using that little shaded red to make the YZ plane, but there's a little bit of work that you have to do before you're ready to use it. Whereas if you project onto your XY plane, you actually are ready to go straight away. You don't have to do any work. So I'm rather going to go for that trapezium in the XY plane because there's no thinking required. I already know everything about it. Whereas the YZ one, there's something I don't know and I'd have to work it out first. Okay, so that's going to be my R. Cool. I'm going to need a conversion factor. The conversion factor, because I'm projecting onto XY, I need to make Z the subject. Z the subject of my surface equation, so it's going to be the square root of 1 minus x squared. I don't need to worry about plus minus. This is in the first octant. Z is positive. A minus in front of that square root would have been the part of the cylinder that was under the xy plane, and I'm not including that. So my x derivative is going to be, let's have a look. It's going to be that. Now, in yesterday's second period, some people were, I'm not sure which problem it was they were working through, but this kind of derivative was popping up in quite a few people's working in second period yesterday, and pretty much everybody was forgetting their chain rule. When you differentiate that, that's 1 minus x squared to the power of half, so you bring your half down and subtract 1. Okay, fine, everybody gets that bit, but then you still need to multiply by the derivative of the inside part. So you have to multiply by minus 2x. My y derivative is just 0. Okay, cool. What else do I need? Oh, I still need my normal. So I'm going to take my surface equation and I'm going to make sure that all my variables are on the same side of the equal sign. And I'm going to work out grad of that thing that's on the left there. Let's have a look. If I wanted to be completely fussy about this, I'd invent a new function and I'd give it a name. And let's say there was a new function I've just invented called g is my surface equation with all of the variables on the same side. So grad of g is going to be 2x, catch up with me stylus, thank you, 0 to z, and my normal is going to be grad g over mod grad g, which is going to be 2x 0 to z over the square root of 4x squared plus 4z squared. Sure! My goodness. My little side of the page scribbles are quite substantial. Question?
If you didn't give it the name G, what would you use?
I would be quite happy for you to brackets the bits that I'm happy for you to leave out. I'm happy for you to leave that out. I'm happy for you to leave that out. I'm happy for you to leave that out. And for you to just put that and work out the grammar of that. And you're dealing with the grammar of this morning. So you don't have to do any of that stuff that I've put in red brackets. I'm just being really pedantic here. The thing that you're aiming for is that normal. Okay, cool. So that's like the stuff that you scribble down the side of the page in pencil, and here we go is the actual problem. I'm going to move my equals over there because I know I'm about to take up a lot of space. I'm going to integral over r. What's v? V is 1 over x, y, 5, dotted. Dotted with my normal. My normal is 2x, 0, 2y over the square root of 4x squared plus 4. Sorry, z. Oops, it isn't. And then I have my scaling factor. My scaling factor is 1 plus the 1 derivative squared. Let's have a look. The 2's will cancel. I'll have x squared. Oh my goodness. I'm going to move that 2. That's the... Whew, my goodness, it's a bit squashed, isn't it? So that over there is my zx squared. It's my x derivative squared. Am I right? Yeah. Okay, all right. Let me do a little bit of tidying. Okay, I'm going to do my dot product.
Sorry.
Yes.
What happens to the one prior you making the grad G?
We're not interested in one. We're interested in okay, let's have a look. What order should I do this in? Okay, I'm going to do my dot product. 1 over x times 2x is 2 plus 0 plus 10z. Okay, that's the dot product. 1 over 2x squared plus z squared. You know what? There's some simplification I can do here, but actually it would be better if I did it over here. What I've done here is correct, but it's actually not the most efficient way. Let's go back down to our normal over here. I'm going to tidy it up a little bit. I'm going to take 2 out as a common factor at the top. I'm going to take 2 out of the square root at the bottom. Okay, that already tidies it up a little bit because I can cancel the 2's. But you know what? This is the normal to my surface. everywhere on my surface x squared plus z squared equals 1. X squared plus z squared equals 1 on S. So this is just x0, z. What I'm going to do now is I'm going to rewrite the line above without simplification. Okay, all right. What did I do there? What did I do there? I basically just rewrote the line that I already had, but with the simplification. I simplified it. And if I can a little bit more out of the top, so that line was at the top of the screen, I would actually never have written that. So I would have written that second one. If I noticed the simplification that could have done, which I wasn't really thinking. The more simplification you can do in the stuff that's down the side here, so that by the time you plug it into your flux equation, it's nice and simple. The more you can do of that, the better. Because otherwise you end up with these huge chunky integrals over there with these huge moduli and all sorts of things that rather, if you can simplify the little bits before they all come together, you end up with a much more manageable flux equation. If you leave all the simplification for after all the bits have come together, you can end up with quite a big mess. But that's just a... doesn't matter where the simplification happens as long as it happens somewhere. Okay, now I'll do the dot product. Catch up with stylus. Thank you very much. Yes, here we go. So that'll be 1. The 2 has gone away now, so plus 5z. That's the square root of minus x squared plus x squared. So it's 1 over 1 minus x squared. If I amalgamate those two terms into the square root of that. Okay, lovely. I'm now going to put in some limits for dA is going to break up into dx dy. I don't want a z in my integral. So let's do a few things at once here. I'm going to integrate with respect to y first. Y goes from 0 to 2 minus x. For values of x that go from 0 to 1. 1 plus 5z becomes 1 plus 5 square root of 1 minus x squared. The conversion factor looks like that. Okay, I can do a small amount of tidying up before I integrate. What do I have? I have 1 over square root 1 minus x squared plus 5 equals. Okay, lovely. Now I'm going to integrate. So I ask myself, what did I differentiate to get 1 over square root of 1 minus x squared? And my answer is... So. It will be outside. That's only in the next step. In this step, it will be just y. And all that stuff in the integrand is just a funny looking constant as far as y is concerned. So when I integrate with respect to y, I'm simply going to be introducing a factor of 2 minus x. Okay, all right. What I was writing there was correct, so I'm not... But there was some noises, So this thing here, which is just a funny looking constant as far as y is concerned, doesn't get involved in the integral with respect to y. So I say to myself, what did I differentiate with respect to y to get that funny looking constant? And the answer is funny looking constant times y. So I stick my y and square brackets. Now when I substitute in, I'll bring in a factor of 2. And now I integrate that. Okay, well that first term there will need to be split up into two terms. Dx, let's have a look, equals, and now we have our arc sine. So it's 2 arc sine x. B plus square root 1 minus x squared. Yes. Minus 5 over 2x squared. Evaluate it from 0 to 1. So it's 2 arc sine 1 plus square root of 0 plus 10 minus 5 over 2. Come on, Stacks. Not that hard. It's your job. In and then a subtract, and let's plug in 0. 2 arc sine 0 plus 1 plus 0 minus 0. Okay, equals. Arc sine of 1, that means sine of what gives me 1? Pi over 2, cool. So this is 2 times pi over 2. Plus 10 minus 2.5. 7.5, well, that's supposed to be 20 now, so it's 15 over 2. So that's plus 15 over 2. And then arc sine 0 means sine of what gives me 0? And that's 0. So what do I have there? I have pi plus 15 over 2 minus 2 over 2. It's 13 over 2. There you go. Sorry, that's come out a bit funny in the writing. There we are. 13 over 2. Is that readable? I hope so. Okay, so that's pi plus 13 over 2. So that's the final answer. Okay, in that particular test, how many marks was that? That was a 9-mark question. That was a 9-mark question. Let me guess where the marks were. So I realize people are still writing down. I will scroll to the bottom. But let me just do a bit of mark allocation. Okay, I'm guessing here, but I'd imagine there was 1 mark for, at least 1 mark for a diagram, 1 mark for knowing the flux equation, 1 mark for the conversion factor, 1 mark for the normal, maybe even 2 marks for the normal. Let's have a look. 1 for replacing the z, 2 for the thingies, the limits of integration. How many do we have so far? 1, 2, 3, 4, 5, 6. That leaves 3 marks. From here on down, there would only have been 2 marks. So where does that last mark go? Probably to simplifying the normal. So there was probably for mark for the dot product. That's just embarrassing. No, I'd guess it's 2 marks for the normal because there was a little bit of work going into the normal. Let's have a look. Oh, yeah. I didn't count that. So you're right. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right, it is only 1 mark for the normal. Okay. So that's how the marks would generally go. So that's a 9-mark question. Okay, let me go down to the bottom, and there's some of you still copying down. Extremely likely that you'll get a question like that in class test 2. Slightly less likely that you'll get a question like that in the exam, because by the time we get to the exam, you'll have done more stuff, and there's bound to be a flux question in the exam. It might be this kind. It might be this kind with a twist requiring a variable change, but more likely it'll be a divergence theorem problem, because divergence theorem problems also involve flux. 100% sure you'll get flux in the exam, but there are options how it might appear. But class test 2, I'd put good money on there being a question like this in. Actually, I wouldn't. I don't put money on anything. But no. But I would be quite sure. Okay, so you give it a go. Try number 35. And 35. I'll give you the answer so you can check yourself. Okay, I was just demonstrating here that when you work out your grad, there are two options of how you cluster the variables together on the same side of the equal sign, and the one you want is the one that gives you the correct sign of z. Okay, so here we're wanting upwards, we're wanting positive z component.